In this video, we will introduce the concept of an antiderivative and an indefinite integral. So we call big F of x the antiderivative of little f if the derivative of big F is equal to little f. So an antiderivative, as the name suggests, is undoing a derivative. So for example, if we think of x to the fourth playing our role of the big F of x, we're claiming that its antiderivative, or an antiderivative, is 4x cubed. And the reason this is true is because the derivative of x to the fourth by the power rule is 4x cubed. Additionally, we say that if we have any antiderivative big F plus c is called the general antiderivative of f. And it turns out that if you're starting off with a function little f, any antiderivative of it can be put in this form. So let's kind of just check and see why that is an antiderivative. If we differentiate x to the fourth plus c, where c is representing an arbitrary constant, we have the derivative of x to the fourth, which is 4x cubed, plus the derivative of a constant, which is 0. So an antiderivative would certainly have this form x to the fourth plus c. Now, in terms of notation, we need to introduce something called an indefinite integral. So if f of x, big F of x, is an antiderivative of little f of x, we use this notation squiggly sign little f equals big F of x plus c. And this is called the indefinite integral of f, and this symbol is called the integral sign. We also refer to this function that is inside as the integrand. And whenever we evaluate an indefinite integral, the language we use is we would say that we are integrating the function. So we're thinking that the indefinite integral is just a notation that represents for us kind of the general antiderivative. And using this notation is just something that tends to be convenient. Now, a few basic properties. First, we can undo the power rule. So one thing that we'll be able to easily antidifferentiate would be x to any power. That's going to be 1 over n plus 1, x to the n plus 1. And note that there should be a plus c there. And just to check, note that if you differentiate 1 over n plus 1, x to the n plus 1, the 1 over n plus 1 comes out front, it's a constant. Then by the power rule, you multiply by n plus 1 x to the n, which is just x to the n. So you get back that function little f. The antiderivative of sine is minus cosine plus a constant, and the antiderivative of cosine is sine plus a constant. And just like with the derivative, you can pull constants outside of an integral, and you can break up an integral over a sum or a difference. That is to say that the integral of f plus g would be the integral of f plus the integral of g. So let's evaluate a few basic examples, and here we're going to really focus in on using kind of the opposite of this power rule. So let me remind you that we saw that the indefinite integral of x to the n, and this is as long as n is not equal to minus 1, is 1 over n plus 1, x to the n plus 1, plus c. So in this first example, what we would like to do is use the properties that we saw. We can, just like with the derivative, break this up into two integrals that we are adding together and pull out constants. So we can write this more conveniently as 3 times the indefinite integral of x squared plus 5 times the indefinite integral of x. And now we can apply this opposite of the power rule below to each of these indefinite integrals. So in the first case, we have our value of n is 2. And 2 plus 1 is 3. So we have 3 times the indefinite integral 1/3 x cubed. In the second case, we have the value of n being 1. So 1 plus 1 is 2, so plus 1/2 x squared. And with one of these indefinite integrals, we always finish up with just a single plus c. So 3 times 1/3 is 1, so this is x cubed plus 5/2 x squared plus c. Now an observation that's definitely worth making is, can we check our work to see if we've done this correctly? And the answer is absolutely. And how we check our work is whatever we come up with as an indefinite integral, when we differentiate this, we need to get back the integrand function. So we don't have to double check, but let's go ahead and do so in our first example. So if we differentiate x cubed plus 5/2 x squared plus c, term by term, we get 3x squared plus 2 times 5/2 x to the first, and I'll write a plus 0 where we differentiated the constant. But note, the 3x squared plus 5x is exactly that integrand function. So check. We've evaluated properly. So let's look at the second example. In this second example, it's x to a power. So the value of n in this case is 4/3. And to use the opposite of the power rule here, we need to have n plus 1. So n plus 1 is 4/3 plus 1, which is 7/3. So our rule tells us that this should be 1 over 7/3 x to the 7/3 plus c. And whenever we're dividing by a fraction, we should always rewrite this. Dividing by a fraction is multiplying by its reciprocal. So 3/7 x to the 7/3 plus c. Let's look at one more additional example. Now, note it's not immediately written in the form that we've previously seen, but what we can do is rewrite these things just algebraically. We can say 1 over x squared is really x to the minus 2, and the square root of x is really x to the 1/2 power. And this is the ideal situation to be in. Once we have everything written in terms of these powers of x, we can use our formula that we've now used multiple times. In the first portion, let's go ahead and break this up. The indefinite integral of x to the minus 2 plus the indefinite integral of x to the 1/2. So in the first indefinite integral, we have n is minus 2. So we would say minus 2 plus 1 is minus 1. So 1 over minus 1 x to the minus 1. In the second indefinite integral, n is 1/2. 1/2 plus 1 is 3/2. So 1 over 3/2 x to the 3/2. And then we make sure to include our plus c. So simplifying slightly here, we could write this as minus 1 over x plus 2/3 x to the 3/2 plus c.